Okay, we'll be solving this differential equation with power series. And now let's get to work. Right here for the second derivative, this is going to be the series where n starts with 2 to infinity, n minus 1 times an times x to the n minus 2 power. And then we continue. We will have the minus 2x times the first derivative, and that's the series where n starts with 1 to infinity, an x to the n minus 1 power. And lastly, we have the plus y, which is plus the series where n starts with 0 to infinity. And this right here is just going to be an x to the nth power. And all this is equal to 0. Okay, as we can see, this is the original. Differentiate this one time, we bring the n to the front and the minus 1, right? And that's how we get this form right here. But you know, this right here, the first term is constant. When we differentiate this, we lose that constant, right? The constant becomes 0 for the derivative. That's why the n starts with 1 for the first derivative. And then we differentiate this again, bring the n minus 1 to the front, and then minus 1 to the exponent. That's how we get the n minus 2. And similar reason, we lose a term right here. That's why for the second derivative, n starts with 2, all right? And this is my infinity symbol. Let me just write it down better. Okay, now let's see what we can do next. Well, right here we notice that we have the negative 2x. We can multiply this with that. So let's just multiply the inside of the series notation right here. The series when n starts with 1 to infinity, let me put down negative 2 inside. And then x times this, right? But let me write down the an, x times x to the n minus 1. This is x first, so we add the exponents. Altogether, it's going to be x to the 1 plus n minus 1, which is just n, all right? Okay, so this is what we have for the second term. And that's the third term, and this is the first term. Here, we have to fix the power of x. This is x to the n, this is x to the n, but this is x to the n minus 2. Ideally speaking, I also want to have this to be x to the nth power, right? And this is how we can fix that. And by the way, you see that we took the negative 2 inside, so I will put down a plus right here, okay? Because the negative 2 is already inside. Okay, for this right here, as I said earlier, I want to have x to the nth power only. And hopefully you guys have seen my previous video, okay, for a similar and then a simpler differential equation with power series. So, you know the deal. From n minus 2 to n, what we have to do is, you add 2, right? You add 2 to the n, and then n plus 2 minus 2, you get n. So, for this part, whenever you see the n, you're going to just add 2 to it. So right here, instead of just an, now it will be an plus 2, right? And then right here, instead of n minus 1, now we have to add 2 to that. N minus 1 plus 2 is just going to be n plus 1, right? So let me just write this down. It becomes n plus 1 now. And this n, we add 2 to that, which becomes n plus 2, okay? And this is how we are going to compromise or compensate the plus 2. When you add 2 inside, what you are going to do is subtract 2 here, subtract 2 there. So this right here is going to be the series when n starts with 0, because 2 minus 2 is 0. And then right here, infinity minus 2 is still infinity. So this is still infinity, okay? All right, so that's the fix for the first part. And for the last part, it has x to the nth power already, so we don't need to fix that. We just have to write it down again. So that's the series where n starts with 0 to infinity, an x to the nth power, and this is equal to 0. Okay, keep in mind, we always want to fix x to the power first. Ideally speaking, we want to have x to the n, x to the n, x to the n, okay? And now, we are going to fix the starting n value. As you can see, this is n is equal to 0, n is equal to 1, n is equal to 0, right? We have to bump up. We want to have n is equal to 1, n is equal to 1. We cannot decrease the n right here, all right? Because if you decrease the n right here, you have to fix the exponent here, so that's not good. And this is how we're going to fix the starting value now. Okay, remember the series notation. We are going to plug in n is equal to 0 for the first term into here, and then plug in n is equal to 1, n is equal to 2, and so on, right? So I'm just going to say let n equals to 1, and let me just do this in blue and red. Okay, n is equal to 0. Plugging n is equal to 0 for the first term, and we will get 0 plus 2 times 0 plus 1, and then times a sub 0 plus 2, and then this is x to the 0's power. That's the first term when n is equal to 0. And then you know the next term is going to be when n is equal to 1. And then the following terms x is when n is equal to 2, and so on. All this right here is the same as saying the summation when n starts with 1 to infinity and all that stuff, right? So we can just put that down now. n plus 2, n plus 1, a n plus 2, x to the n's power. So all this is still the same as that, and let me just do a blue underline right here, okay? So, well, actually, let me just box that. This right here is all this, okay? And for the middle term, this is n is equal to 1 already, so I don't have to fix that. So let me just write this down again. We add the series when n starts with 1 to infinity, and the inside is negative 2n, an, x to the n's power. And then for this one, as you can see, n starts with 0. That's no good, but we can just do this to fix that, right? So let's see, when n is equal to 0, we plug in 0 into this n and that n. That would be the first term, right? So we have plus a0 times x to the 0's power. And then anything after that is n is equal to 1, 2, 3, 4, 5, and so on. But we can put them into the sigma notation, right? So we can write this down as plus the series when n starts with 1 now, 1 and after, right? 1 to infinity, and then this, which is the an x to the n. And as you can see, this right here is for this, okay? And all in all, this is still equal to 0. And now what? Well, let's take care of some business. The things that's not inside of the sigma notation, namely this and that, okay? So let's look at this term first. It's pretty much 2 times 1, which is 2, and then 0 plus 2 is 2, but that's a subscript, so we have a2. X to the 0th power is just 1, so this is just 2a2. And then for this, it's just plus a0, because this is just 1, right? So we have 2a2 plus a0. These two terms are not in the sigma notation, right? And if you look at this, that, they are all in the sigma notation. And it's all from n is equal to 1 to infinity. And they all have x to the n's power. So now we can just put them into just one sigma notation, right? So let's do that. We add the series when n starts with 1 to infinity. And let me open a big parentheses. Let me put this down first, which is n plus 2. And by the way, don't multiply this out, okay? Just keep it as how it is. N plus 2 times n plus 1 times an plus 2. I will factor out the x to the n, and we'll put that at the end, okay? So let me just not write this down yet, and I'll continue. This is minus 2n an, and this is going to be at the end later on. And lastly, we have this plus an, right? So we have plus an. And I will close this parentheses, okay, from here to here. And I will have the x to the n at the end. And all this is still equal to 0, okay? And now what? Well, you know, these two terms, they add up to the constant term, right? Because they don't have any x to the whatever power. On the right-hand side, it's always equal to 0. So that means we have the first condition. This plus that must be equal to 0. And let me write this down right here. We must have 2a2 plus a0 equal to 0. And now let's look at this right here. As you can see, this right here is technically just all the coefficients of x to the whatever power, right? And you see, the right-hand side is always equal to 0. So that means each and every coefficient must be equal to 0 as well. So here is the second condition. All this right here have to be equal to 0. So let me put this down right here. We have n plus 2 times n plus 1 times an plus 2. And then this right here, because they both have the an, right? Let me factor it out. And I will do it this way. Let me factor out a negative first, and then let me put down parentheses. And originally this was negative 2n, and now it becomes positive 2n, right? And this was plus 1an, now it will become minus 1, okay? If you distribute, you will see negative 2n and then plus 1. And I will put down the an at the end, like this. And now I'll put this down right here. Minus 2n minus 1 in the parentheses like this, and then an is equal to 0. So these are the two conditions that we have. Let's look at the first one. I am going to solve for the a with a bigger index, namely a2, okay? So that said, we can just minus a0 on both sides and divide it by 2 on both sides, right? So a2 is equal to negative 1/2 a0. This is the first thing that we're going to utilize later on, okay? And likewise, for this right here, we will be solving for the a with a bigger index, which is this right here, an plus 2. So to do that, you see, we will have an plus 2 equal. Move this to the other side. That's why it becomes positive. That's why I factored out negative earlier. It becomes positive 2n minus 1. And I will put on the an on the side later. And I will divide by this, right? So divided by n plus 2 times n plus 1. And now let's put down the an on the side. Okay, this and that is what we need. And another thing that we need is more space to do the work. So now let's get to work. So this is what we have. As you can see, I wrote down the formulas that we got earlier right here, right? The first one, a2 is equal to negative 1/2 a0. As you can see, this is telling us a2 is based on a0. So in that case, we can say that a0 to be arbitrary, okay? And right here, you see, we don't know anything about a1. So in that case, we will also say that a1 to be arbitrary as well. And in this case, a0, a1, they are in fact our constants for our differential equation. This is second order, so we should have two unknown constants at the end, right? It will be the a0 and a1. And anything after a0 and a1, the a2, a3, a4, and so on, right? We will have to use this formula to help us generate. So be sure you put this down right here and set our table with the n values on the side. And now, let's get to work. So in this case, n start with 0, and then you can keep on going. And let me just do 0, 1, 2, 3, 4, 5, 6, and 7. When n is equal to 0, we know right here it will be a sub 0 plus 2, which is a2. Okay? And this is the easiest way that I find to fill in this table in this situation. Just pick a part and then do it vertically. Okay? So you see, I did a2, and now if n is equal to 1, it will be a sub 1 plus 2, which is a3. And you see the pattern. The next one is going to be a4, and then a5, a6, a7, a8, and at the end is a9. Right? So this is my a, and then this is my 9. And then equal signs, equal sign, equal signs. Just, keep on going like this. Okay? This is the fastest way that I find. Next, you see, plugging 0 into the top. 2 times 0 is 0. Minus 1, we have negative 1. Once again, just do one part at a time. Next, we have 1 plug into here. 2 times 1 is 2. Minus 1 is 1. So we have positive 1. And then 2 right here. 2 times 2 is 4. Minus 1 is 3, right? And can you guess what's next? Well, you can try it out first. It's going to be 3 into here. 2 times 3 is 6. Minus 1 is 5. What's next? You have 1, 3, 5, 7, right? And then 9, and then 11, and then 13, right? And then fraction bar, 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 fraction bar. Okay, when n is equal to 0, plug into here, we will have 2. And don't multiply it out, just leave it as how it is, okay? This is 2, and then plugging 1 into here, we get 3, and then 4, 5, 6, 7, 8, 9. Lastly, plugging 0 into this part, we get 1, and then plugging 1 into here, we get 2, and then 3, 4, 5, 6, 7, 8. And then, of course, we should also put down the a's whatever. So plugging 0 in here, we get a0, and then keep on going. a1, A2, A3, A4, 5, 6, 7, all that stuff, okay? So it's not that bad. Okay, now, this and that, well, A0, A1, they're arbitrary, so we just leave it as how it is. And now if you look at what A4 is, A4 is based on A2, and let me just color this, right? This is my A2 right here. And what's A2? We have to look back to here. So in other words, this is equal to 3 over 4 times 3. And yes, I did not reduce anything for a good purpose. Let me just write down the A2, which is this right here. We multiply by negative 1 over 2 times 1. And then we have the A0, okay? And then for this one, we have A5 is based on A3, and A3 is that guy, right? I'll do this one in blue. So if you look at this is A3, and this is going to be equal to 5 over 5 times 4. A3 is that, which is 1 over 3 times 2 times A1, right? And then we'll just do this. Next, A6, it's based on this is 4, so let me just call this in red, A4, right? This is my A4. So here we have 7 over 6 times 5. A4 is this guy. So just write it down. Okay, so be patient. This right here, 3 over 4 times 3, and then times negative 1 over 2 times 1, and then this is A0. And next one, we have A7, which is based on A5, but let me write down the 9 over 7 times 6. And then for the A5, we look at this right here, right, which is this part. So you just write it down, and once again, be patient, times 5 over 5 times 4 times 1 over 3 times 2, and then this is A1. And then just do 2 more, okay? So this is a lot of fun, I guess. 11 over 8 times 7, and this is the A6. A6 is right here, all this right here. So we multiply by 7 over 6 times 5 times this, which is 3 over 4 times 3 times negative 1 over 2 times 1, and then we have the A0. Lastly, on the table, we have the A7 here. This is equal to 13 over 9 times 8, and then A7 is all this right here, right? Okay, so we have 9, this is 9. 9 over 7 times 6, and then times 5 on the top over 5 times 4 times 1 over 3 times 2, and then this is multiplied by A1. And now we have all the ingredients to write the solution for that differential equation. And remember, the solution is in the form of y equals to the series when n starts from 0 to infinity, an times x to the nth power, right? And this means we will have a0 plus a1 times x to the first power plus a2 times x to the second power, and so on forever. And as you can see, we have a0, 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 a0. I will put down all the coefficients that has the a0 in red, and then all the coefficients that has the a1 in blue, just like what I did right here, okay? So now let's get to work. The first term is going to be just a0, and that's a constant term. And technically, we multiply this by x to the 0th power, but that's 1 anyway, right? And then we add, the next term is going to be a1, and I will put that down in blue. But we will have to multiply this by x to the first power, all right? And then we continue, we add a2 times x to the second power, and a2 is this. And let me just write down negative 1 on the top over, and on the bottom you see 2 times 1. I know that's 2, but let's put down 2 factorial because you see all these numbers right here, right? So let's write down 2 factorial, and we have to multiply this by a0 and also x to the second power because that's a2, right? So x to the second power, and then just keep on going. Next one, we have to multiply by a3, which is this, which is 1 over 3 factorial in the denominator, and then we have the a1 right here, and then we have to multiply by what? We have to multiply by x to the third power, right? Just like this. And what's next? Plus A4, which is all that. And let me write it down like this. Plus, and I will put down negative all the way in the front, like this, and then 3 times 1, like this. And then on the bottom, it's going to be 4 factorial. So we have this over 4 factorial, and then we multiply by A0, and then we have the x to the 4th power. And I'm going to do the next one, plus A5, which is this right here. So we will have 5 times 1 on the top. And let me just keep it as how it is. Over 5, 4, 3, 2, 1, right? So let's put down multiply by 1. So that would be 5 factorial. And then we multiply by A1. And we multiply this by x to the 5th power, right? And I am going to go to A6. And you see, when you're doing this kind of things, just be patient. So let's put down plus A6, which is all that. On the top, let me write down the negative first. So we have negative 7 times 3 times 1 over, on the bottom is just going to be 6 factorial. That's nice. And then we have the A0. And this is A6. That means we multiply by x to the 6th power. And then we just keep going. Plus A7, which is all that. Let me write it down as 9, 5, 1, multiplying on this on the top, and then down the bottom is pretty much 7 factorial, and then multiply by A1, and then we put down x to the 7th, and then 2 more. Here we have negative all the way in the front, and then 11 times 7 times 3 times 1 over, the bottom is going to be 8 factorial, and then we have the A0, and then this is x to the 8th power, and then lastly we add A9, which is all that. I will write down 13 times 9 times 5 times 1 over 9 factorial. And then we multiply this by x to the 9th power. And then this keeps on going forever. All right, so this is pretty good. It's the expanded form, but we can make it better. We are going to put all the terms that has the A0 first and then factor out all the A0, right? So that's all the coefficients in red. And let me do that right here. So this is going to be, let me put down the A0 first, and I'll open the parentheses. We factor out the A0, so this is going to be 1. And let me just write it down. Let me just write down everything in red. 1. And then this is going to be negative 1 over 2 factorial. A0 is out already, and we have x to the 2nd power. And then this is the next term. We have minus 3 times 1 over 4 factorial, and then A0 is out, and then this is x to the 4th power, and then we have that, so minus 7 times 3 times 1 over 6 factorial, and then A0 is out, and then we have x to the 6th. This one, minus 11 times 7 times 3 times 1 over 8 factorial, and then multiply by x to the 8. So this is pretty much all the terms that's going to be having the A0, right? And you know the next one is going to be minus, so it's going to be minus whatever, and forever, right? And then we'll put down all the terms that has the A1 in blue. And let me just say plus A1, parentheses, first right here it's going to be x, next it's going to be this, plus 1 over 3 factorial. A1 is out already, so we have just the x to the 3rd power. And next is that. And let me just put down plus 5 times 1. And then on the bottom is 5 factorial. And then this is x to the 5th term. And we have this right here, plus 9, 5, 1 over 7 factorial. And then x to the 7th, and then one more, plus 13, 9, 5, 1 over 9 factorial. X to the 9th power, and this keeps on adding forever. All right? So I will call this the expanded form, and this is usually more preferred than this, okay? And we can make this to the ultimate best. We are going to find a formula for all these coefficients, right? Whenever possible, and we'll put that into the sigma notation, right? So that's the last thing that we'll do. So here is the deal. Let's try to write a formula for the red part first. All the way in the front, we have A0. So there's absolutely no argument on that. And now let's see if we can write a formula for this. Okay? Well, is there any pattern? It seems like on the bottom is 0 factorial. By default, that's 1. And then 2 factorials, and then 4 factorial, and then 6 factorial, 8 factorial. So I have all the even factorials, right? However, and also unfortunately, on the top, this and that is 1 and negative 1. And this is negative 3 times 1. This is negative 7 times 3 times 1. This is negative 11 times 7 times 3 times 1. Can you guess the next term? It will be negative 15, 11, 7, 3, and 1, right? Well, you see, this is 3 to 7, it's adding by 4. And then from 7 to 11, it's adding by 4. But the issue is that from 1 to 3, it's only by 2, right? So in terms of the numbers that you are multiplying, this add 4, but this is adding 2. So this is how we have to do it. From here to here, from 1 to the extra 3 right here, I don't really have a nice pattern for that. So I will write these two terms first, separately, okay? So I will write it down as 1 minus 1 over 2 factorial x squared. And if you would like, of course, you can just say that's 2 on the bottom. And then, first of all these are just minus, minus, minus. So I will just put down a minus right here, all right? And then we'll minus, and we'll try to put this in the summation notation. And now, here is the deal. In order for us to use the sigma notation, we have to put an index right here, right? And many times, the textbooks will just use n is equal to whatever. But when they use n right here, this n is very different than these n's that we used earlier. And I find it's kind of confusing. So the way to get over that is we can use another letter. Let me say k, for example, right? K equals to something to begin with. And now you can see this letter k is going to be different than that for sure, right? And now I have to go back to here and then try to write a formula in terms of k. And the first question is, k start with what though? Well, this was my first term and that was my second term. I should say right here that's labeled k is equal to whatever. And when we're doing power series, we like to start with 0. So let me put this down as k is equal to 0, and this is k is equal to 1, and then k is equal to 2, and then k is equal to 3, and so on, all right? And once again, even though I'm using n, but when we are trying to close this into a sigma notation, you get to use any letters that you want for the index, all right? Anyway, so these two terms are okay because I just write it down separately. And now, let's take a look. When k is 2, on the bottom, I have 4 factorial. When k is 3, on the bottom, I have 6 factorial. And then you know this is just going to be twice as many k and then factorial, right? So we know it's going to be k start from 2. And then the bottom is going to be 2k in the parentheses, and then we have the factorial, okay? So once again, if you see when k is equal to 4, which is going to generate this term, 2 times 4 is 8, and then we have the factorial. And I start with 2 because I want to just write down the sigma notation for this. And then I factor out all the negative in the front already, all right? And now, let's put down the x to the power, because that's also just as easy as this. You see, when k is 2, this is 4, 3 is 6, and so on. You know it's the same thing as x to the 2k power, like this. And now, what's the numerator? This is the tricky part. Well, as we discussed earlier, you see, from 1 to 3, I know it's adding up by 2. But then from 3 to 7, it's adding up by 4. From 7 to 11, it's adding up by 4, right? So on the numerator, from here and after, I'm going to erase the 1, all right? I'm going to erase the 1, like this. And if you just focus on number, the first number is 3, the next number is 7, and then the next, I should say, the next new number is 11, and so on, right? And if you just look at this number, every time you go up by 4. So what we can do is, let me put this down in black. I start with 3 times the next number is 7, and the next number is 11, and then so on, so on, so on. And we know we must stop at somewhere, right? So let me put parentheses, and we have to figure out a formula for the last number that we have to multiply right here. So to do that, we have to go back to here again. And you see, we have to write a formula. You see, this is 3, and then 3, 7, and then 3, 7, 11. And then the next one is 3, 7, 11, 15. Okay, this is how you can do it. Every time you know the new number is going to be increased by 4, right? Just like from here to here, the new number is 11, we go up by 4. And this is telling us that we have an arithmetic sequence. So in that case, the formula is going to be 4, okay? The common difference, which in our case is 4, times whichever the variable that we're using, which is k in this case, right? And now we just have to figure out if we have to add or subtract a number right here. To do so, the easiest way is just look at an example right here. When k is 4, the last number that we are multiplying, or the new number that we are multiplying, is 11. 4 times 4 is 16 already. How can we get 11? Well, 16 minus 5 is 11. So therefore, it will be 4k minus 5. This is the formula for the last number that we have to multiply. And we can use this formula to check if it will work for this. When k is 3, 4 times k, 4 times 3, which is 12, minus 5 is the 7, right? So this is pretty much it. And in fact, we can use the capital Pi notation to write a closed form for this. But let me do that at the end. This is acceptable, and this is also good enough for now. Anyway, this is the red part, all right? Therefore, I'm going to close this. And now let's put down the formula for the blue part. So we add, and then let me just write down A1. And now we'll be doing the same thing, but just for the blue part right here. Okay, can we write a formula for all this? On the bottom, it's nice. It seems that we have the factorials, right? But on the top, it's the same issue again. Okay, this is 1, this is 1, and then this is 1 to 5, which is you add 4, and then plus 4 plus 4, plus 4 plus 4 plus 4, right? But then 1 to 1, cannot really do anything. So I'm going to write a formula for these terms only. Leave the x right here alone, right here, okay, without putting it down in the sigma notation. So let me put down the x first, and it's all adding, so I'm just going to put down plus, and I will put down all these terms right here in the sigma notation. Okay, once again, you can use either another letter, or you can use k, or you can use n. Seriously, up to you, right? But in this case, let me just use, let's say, m. Just use another letter, so in fact we can feel better. And we like to start with the first term being 0. So this right here is technically m equal to 0. And then you know the deal. This is m equals to 1, and then m is equal to 2, m is equal to 3, m is equal to 4. And when you're looking at textbooks or other people's videos, they may still be using n. But you have to just remember that every time the n's are different, all right? Okay, so I want to write a formula for all this. That means m start with. That means m start with 1, and then of course we go out to infinity. And for the bottom, we have the factorial, and you see when we have 2, we get 5. When we have 3, we get 7, right? You know that's the numbers, right? So you can just do 2 times the m value, and then plus 1. 2 times 3 is 6, plus 1, we get a 7, and put a factorial, right? So therefore, this is going to be 2m plus 1 in the parentheses, and then put a factorial at the end like this. And for the powers, it's just same as the factorial right here. So this is x to the 2m plus 1 power. Let me just close this so we can feel better. So now let's check this out. We're trying to write a formula for all these terms, right? So you see we have 1, 1, 5, 1, 5, 9, and so on, right? So it begins with 1, and then the next number is going to be multiplied by 5, and then the next one is going to be 9, and so on, so on, so on. And then just like that, we have to write a formula for the last numbers that we are multiplying right here. Okay, once again, go up by 4, go up by 4. So we know it's going to be 4 as a common difference. As a common difference times whichever the letters that we're using, which is the m. And then you have to see, for example, when m is 3, the last numbers that we are multiplying is 9. 3 times 4 is 12 already. 12 minus 3 will give us 9, right? So it will be 4m minus 3. Okay? So double check. 4 times 4, which is 16. 16 minus 3 give us the 13. So that is the formula for the last numbers that we are multiplying. And this right here is it, okay? So first of all, let me just box all this right here for the answer. And once again, if you use k right here, or m right here, or n right here, doesn't matter. And before we go, let me show you guys this. As you can see right here, we are just multiplying a bunch of numbers that they have a pattern, right? Remember, for a series, we are just adding up a bunch of numbers that they have a pattern. And you see, we use the sigma notation for the sum, for the series, right? So right here, let me introduce you guys to the capital Pi notation for the product, if you haven't seen this already. So right here, let me put this down. Another way to represent 3 times 7 times 11 times ... up to 4k minus 5, it's the following. We can use the capital Pi notation to represent the product of a bunch of numbers that they have a pattern, right? And I'm going to use another index. I will just say this is I. And earlier, I began with 2. I will just keep it as 2, right? And this is saying I goes from 2. And the last term that I want to have is k. I just want to have k many terms. So not infinity right here, right? And I just have to put down the formula that I got right here, which is 4i minus 5, like this. So what this means is that when you see the pi, you are going to keep multiplying. First term, you're plugging I is equal to 2 right here. 4 times 2 is 8, minus 5 is 3, that's the first term. And then you multiply when I is 3. 3 times 4 is 12, minus 5 is 7. And then so on, so on, so on. You multiply the last term, which is k right here, which is the 4k minus 5 right here, all right? So if you would like, you can put this right here for this, and likewise, you can do the similar things for this product as well. Anyway, this is the longest question I have done in a video, and this right here is it.